Today we're going to discuss linear transformations. But first, let's do a quick review of maximal linearly independent subsets. We have two results that we want to remind you of. The first gives us a quick way of determining when a set S is a linearly dependent set. Let's say that V is a vector space and let T be a finite subset of vectors. Let's choose a vector lowercase v that is not in T, and let's let S be T union with this vector. We'll say that S is a linearly dependent set if and only if our vector lowercase v is an element of the span of T. Next, we have a way of determining what the dimension of a space is. Again, say that V is a vector space, but now say that V is spanned by some finite set S. First, there exists a basis beta for V that is contained in S. Second, every basis beta of V has the same number of elements. We'll use this number to determine the dimension of V. Finally, we can relate the existence of a basis for a vector space V to that of any subspace. We have three statements. Let W be a subspace for V. And let's assume that V has a finite basis beta. First, W has a finite basis T. Second, the dimension of W is less than or equal to the dimension of V. And third, the dimension of W equals the dimension of V if and only if W equals V as vector spaces. We also want to do a review of functions before we go into linear transformations. Here we're just going to review some notation and some definitions. Let x and y be sets. We'll use the notation f colon x arrow y, read as f goes from x to y, to denote a function. We'll write f colon x arrow y to mean f of x equals y for each element lowercase x in the set capital X. The set x is called the domain of our function f, whereas the set y is called the codomain of our function f. Given such a function, we'll denote the following set as the range of f. Sometimes we'll call it the image of f. This consists of those elements lowercase y in the set y such that lowercase y equals f of x for some lowercase x in our domain capital X. Notice that the image of f is a subset of the codomain y. Similar, given any subset U of our codomain y, we'll denote the following set as the preimage of f, or if you will, the inverse image of f. This is the set of lowercase x in the domain capital X, such that f of x is an element of our given subset U. This is a subset of the domain X. As a warning, this f to the minus 1 is not a function. Here we're just using the notation to denote that we care about the elements in the domain that correspond to certain elements in the codomain. We can put all of this together in the following diagram. The red that you see over on the left is our domain, and the blue that you see over on the right is our codomain. The yellow that you see on the right is the image of our function f. The arrows here going from lowercase x to lowercase f of x tell us what's happening with the individual elements. Let's let f be a function again. We want to define some words. We'll say that our function is well defined if f of x1 equals f of x2 whenever x1 equals x2. Let's give an example of this. Consider a function f which goes from the rational numbers to the integers, defined by taking a ratio p over q and sending that to the numerator p. Unfortunately, this function is not well defined because while the fractions 1 over 1 and 2 over 2 are the same, their numerators are different. That is, f of 1 over 1 is just simply the numerator 1, yet f of 2 over 2 is the numerator 2. Of course, the way that we can make this function well-defined is placing in the condition that p and q, the numerator and denominator, are relatively prime. We'll say that our function f is 1 to 1 if f of x1 does not equal f of x2 whenever x1 does not equal x2. Sometimes we'll call this an injection. Here's an example. Consider the function mapping from the real numbers to the real numbers defined by sending x to the real number x squared. This map is not 1 to 1 because while x1 equals negative 1 and x1 equals negative 1 and x2 equals plus 1 are different, we see that the image f of x1 equals f of x2 equals 1. We'll say that our function f is onto if for each lowercase y in the codomain y, there exists a lowercase x in the domain x such that f of x equals y. Sometimes we'll say that our function f is a surjection. Here's an example. Consider the same function we had before, mapping from the real numbers to the real numbers, defined by sending x to x squared. This map is not onto because there is no real number x such that f of x equals negative 1. Simply put, there's no real number x such that x squared equals negative 1. Finally, we'll say that our function f is both 1 to 1 and onto if it is both an injection and a surjection. Sometimes we'll call this a bijection. As a word of caution, we're going to reserve the word isomorphism for later on in the course when we introduce maps which preserve certain given binary operations. Here's a diagram and some examples to help explain some of the words that we've introduced so far. Consider the following map. Recall that capital X is the domain and capital Y here is the codomain. Inside of the domain, we have the numbers 1, 2, 3, and inside of the codomain, we have the letters A, B, C, and D. You'll see here that our map is well defined because for each element, for each number in the domain, we have at least one letter in the codomain. This map is 1 to 1 because each element in the domain maps to exactly one element in the codomain. However, this map is not onto because there exists at least one element in the codomain, namely the letter C, which doesn't come from any of the numbers in the domain. Again, our map here is well defined, 1 to 1, and not onto. So we would say that this map is not bijective. Here's a second example. Now we have the numbers 1, 2, 3, and 4 mapping to the letters B, C, and D. Again, this is well defined, but this is not 1 to 1. Notice that the two numbers 3 and 4 map to the same letter C. This map is onto because each of the letters B, C, and D comes from at least one number. Again, our map is well defined, not 1 to 1, and onto. So again, this map is not bijective. For the last example, consider the case here where we have our 4 numbers in the domain and our 4 letters in the codomain. We see that this map is well defined, 1 to 1, and onto. Again, each of the 4 letters corresponds to exactly one of the 4 numbers. So by definition, this last example is bijective. Now that we have our various definitions, we can go over the concept of a linear transformation. Say that we have 2 vector spaces, V and W. Here we'll try to be very precise as to which operations we're using. We'll use circle plus and circle dot for the vector space V, and we'll use square plus and square dot for the vector space W. We'll say that a map T is well defined, just like before, if T of x1 equals T of x2 whenever x1 equals x2. We'll say that our vector space V is the domain and our vector space W is the codomain. Given such a well-defined map T, the following 2 statements are equivalent. First, our map preserves vector addition and it preserves scalar multiplication. That means the following. Given two vectors x and y in V and a scalar c in F, first we want t of x plus y to be t of x plus t of y, and second we want t of c times x to equal to c times t of x. This is equivalent to the second property, which is given any collection v1, v2 through vn as vectors from capital V, and any collection of scalars a1, a2 through an in F, we have the following expression. Here we have a linear combination involving the a's and the v's. The image of that, after we apply t, should be another linear combination now involving the a sub i's as well as the t of v sub i's. For the second property, we would say that t preserves linear combinations. A well-defined map satisfying either of these equivalent definitions is said to be a linear transformation. Let's try to go over the proof of this to get a better idea of what this says. First, let's assume that t preserves linear combinations. We're going to show that t preserves vector addition as well as preserves scalar multiplication. To this end, let's pick two vectors x and y and a scalar c. The whole idea here is that if we take a look at x plus y, we can also express that as a linear combination. Namely, it's 1 times x plus 1 times y. Well, according to property 2, this should be the same thing as 1 times t of x plus 1 times t of y. And of course, if we multiply by 1, we're not changing much. So we see immediately that t must preserve vector addition. Similarly, t preserves scalar multiplication, but this simply follows directly from the assumption that t preserves linear combinations. Here we just have a linear combination consisting of one vector. Conversely, let's assume that t preserves vector addition as well as preserves scalar multiplication. We must show that t preserves linear combinations. We're going to prove this by induction by considering the following proposition. For any linear combination a1 v1 plus dot 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 an vn, t of that is the linear combination a1 times t of v1 plus dot 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 an times t of vn. To prove this by induction, first we must establish the base case. When n is equal to 1, we know that this is true because we saw before that this is equivalent to saying t preserves scalar multiplication. So let's assume the inductive hypothesis, that is that our statement p of n0 is true for some positive integer n0. Now we must perform the inductive step, so consider the next p of n0 plus 1. Let's choose a collection of n0 plus 1 vectors as well as a collection of n0 plus 1 scalars. We'll express our linear combination as x plus y, where x consists of a sum of the first n0 vectors, and y will just consist of the final vector involving v n0 plus 1. Now we can express everything using our inductive hypothesis. That is, let's take a look at the following linear combination. Here we have t of the sum of n0 plus 1 vectors, which we can write as t of x plus y using associativity. Now we use the fact that t preserves vector addition, and we simply substitute using the inductive hypothesis what t of x is. Now we use the fact that we can simply move around our parentheses a little bit to see that this really is just the sum, which is a linear combination as what we desire. Hence, proposition p of n0 plus 1 must also be true. But this means that our proposition p of n must be true for all positive integers n. Let's end by going over an example so we can get a better idea of what this looks like as we bring it a little bit more down to earth. Let's say that V and W are both R2, namely the real plane. Let's fix four scalars, A, I, J, and let's consider the following map. This map T takes a vector x, y, and it sends it to the following two-dimensional vector. A11x plus A12y, A21x plus A22y. This 2 vector, we're going to write in a strange way. We'll write it as a 2 by 2 matrix times a two-dimensional vector xy. This 2 by 2 matrix times this vector we've now defined as this two-dimensional vector. We claim that this T is a linear transformation. In order to do this, we first must show that T preserves vector addition. So let's start by taking two vectors from R2 and adding them together. Now we'll simply substitute back in the definition of T from above, and using distributivity, we can now write this as the sum of two vectors again in R2. Finally, we just use the definition of T once more. We see now that T must preserve vector addition. Next, we must show that T preserves scalar multiplication. Here we'll take a scalar multiple of the vector x1, y1, and we'll just use the definition by scaling each of our coordinates. Now we substitute using the definition of T, and we realize that we can just pull out the scalar from each of our entries, again using the distributivity laws. But from the definition of T, we see that this is just C times T of x1, y1. So we conclude that T must indeed be a linear transformation. The whole idea of this example is to show that if we're given a 2 by 2 matrix, we can always write down a linear transformation. We're going to see later that the opposite is also true. If T is a linear transformation, V is the collection of n-dimensional vectors, and W is the collection of m-dimensional vectors, then we'll always associate to T an m by n matrix A. We'll come back and we'll discuss this later on in the course. Thanks for watching.